I saw this question on YouTube, and I have my way of doing it, so I want to share it with you. Now, given function f from real numbers to real numbers, and x is not a zero, we are looking for the interval of looking for the integral from 0 to 1 f of x dx when this is given. We are given function equation. We are looking for that. Okay, now my method starts with this. I want to create a new function equation by replacing x by 1 minus x, 1 over 1 minus x. We replace by this to create a new functional equation. So this becomes 1 over 1 minus x plus f. This I have to work out carefully because I don't want to make a mistake. Now, when x is replaced by that, so we have a 1 minus 1 over 1 minus x. This is 1 minus 1 plus x. So it equals to x. So this becomes x is equal to arctangent 1 over 1 minus x. I call this equation 1, this equation 2. Now here, x is not a 1, right? X cannot be a 1. But in our requirement, see, we are interested in the interval from 0 to 1. Therefore, 1 is not included. 1 is not there. From this requirement, actually, our domain is an open interval from 0 to 1 to real numbers. That is the function we are interested. Okay. So this makes sense because 1 is not in our domain for this particular integral. Now, then I create another function equation replacing x by 1 minus 1 over x. X is not 0, right? That's there. Now, then we have a new function equation, which is f of 1 minus 1 of x plus f. This I have to work out again. Replace this one, right? 1 minus 1 of x. Now I replace x by this. So this is 1 minus 1 over 1 minus 1 of x. So this one is equal to 1 minus x, x minus 1, isn't it? So this one is equal to x minus 1, x minus 1 minus x. So this one is equal to minus 1, x minus 1, which is equal to 1 over 1 minus x. So this becomes that. So we have f1 minus x is equal to arctangent 1 minus 1 of x. I call this one equation 3. Now I have 3 functional equations. If I add equation 1 to equation 2, equation 1, add equation 2, then minus equation 3. See, something happening. This plus this minus that. So I get 2 function f of x, this plus this, right? And this plus this minus this, they all cancel out. So the left-hand side is just 2 f of x is equal to arctangent x plus arctangent 1 over 1 minus x minus arctangent 1 minus 1 of x. See, I got a new function equations, which is a good, because from that we can find what we want. Therefore, 2 integral from 0 to 1 f of x dx is equal to integral from 0 to 1 arctangent x dx plus integral from 0 to 1 arctangent 1 over 1 minus dx minus integral arctangent 1 minus 1 of x dx. Good. That is the idea of to create two more functional equations so that we can find out what we want by integrating these three integrals. I call this is I1, this is I2, this is I sub 3. So I just simply do one by one. And I1 is equal to I1 this 0 to 1 arctangent dx. Of course, we are using by parts, right? This is u, this is dv. So this is v times u from 0 to 1 and the minus integral 0 to 1. V is the x, right? Du is the derivative of arctangent, which is 1 plus x squared dx. And this one is quarter pi. And minus, that one is equal to 1 plus x squared d 1 plus x squared. Now you get a 2x dx. I got a x dx. So I divide it by 2, and I got equal. So this one is equal to quarter pi minus 1/2 from 0 to 1, right? Log 1 plus x squared from 0 to 1. So this one is equal to 1/4 pi minus, this is log 2. This is a square root, right? Minus square root 2. Yeah. So that is my I1. Okay, good. And I2. I2 is this integral. From 0 to 1 arctangent 1 over 1 minus x dx. Yeah, obviously that I'm using substitution. Let the u be 1 over 1 minus x. And we can find x is equal to 1 minus 1 over u. So my integral becomes, when x equals to 0, it's 1, right? It's 1. Yeah. When x equals to 1, this should be infinity. This will be arctangent u and d dx. Okay. And this is equal to, from 1 to infinity, arctangent u. This, same thing as d negative 1 over u, right? They're same. Now I can use by parts again. So this is u, this is u, this is dv. This is arctangent u or from 1 to infinity plus integral v. V is a 1 over that, right? Change the sign and for negative. And the derivative of the du is equal to 1 over u squared plus 1 du. Yeah. Okay, good. This is equal to, now, this is infinity to 0, right? When x, this is 1, this is negative, negative again, quarter pi positive. This is become positive quarter pi. For that one, we use the partial fractions, right? Well, I suppose you know partial fractions, so I can omit some detail. This is equal to 1. This is a u negative. Okay, simply use the method to determine the coefficients. So this one is equal to 1 quarter pi plus log u, right? Yeah. Minus this is equal to the u squared plus 1 over u squared plus 1 times half. Yeah. From 0 to, this is from 0 to 1 key. Then this is 1 quarter pi plus, this is, these two log can combine. One log, this is positive, this is negative, square root this here, from 1 to infinity. Yeah, good. And then this is equal to quarter pi. This is when you take infinity as 0, because log 1 is 0. The other one is plus log 1 over square root 2, isn't it? Yeah. This is negative. So this is negative, huh? This is negative. I'm sorry. This is negative. Now, this one I can change to positive by flip over, right? So this is plus log 2. Okay. So this is my I2. Now then I3. I3. I3 is equal to this, right? This. Integral from 0 to 1 arctangent 1 minus 1 of x dx. That is this one. Okay. So obviously that I've been using substitution. Let the v be 1 minus 1 of x. Then my x will be 1 over 1 minus v. Yeah. Then I change this integral into when x is 0 is a negative infinity. When x equal to 1, it's a 0. This becomes arctangent v. Dx will be this d1 minus v, right? The x is this. Now I can use it by parts. This is u, this is dv. So this one is equal to u is this, v is this, from minus to infinity, right? Minus integral v du, v is this, u is the derivative of this one, right? Is equal to, yeah, very good. Now, and this one is equal to, this is 0, 0. When this is infinity, it's also 0. So this is 0. Now, I switch these two. I change the sign, right? Become plus. From minus infinity to 0, this becomes v minus 1. This v squared plus 1. Well, multiplication, okay. Now I'm using partial fractions again. So this one is equal to integral from this to 0. Well, I suppose you know how to do it. So I just skip the steps for finding the coefficient. This is 1, this is minus, this is v plus 1, and times half. Okay, these are just little detail now for determining the coefficients in the partial fractions. Then I got two integrals. And the first one is 1/2 natural log, right? When v minus 1. And this integral becomes 1/2, right? Minus in 0, and v plus this one. And minus again 1/2 for this one, dv v squared plus 1 minus 0, right? For this, I change it to the dv squared plus 1. That will be 2v dv. I got a v, so times half again. Just 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 little detail for the. Okay, then I put a limit later. Okay, this is 1/2 natural log v minus 1. This will be minus half. Yeah, times another half. You have another half. Natural log v squared plus 1. And minus half. This is arctangent, right? Arctangent to v. So all v from minus infinity to 0. Okay. Now then I can combine 1/2 is common factor. natural log v minus 1, and this will be square root, right? Square root. This becomes square root v squared minus plus 1 from minus infinity to 0. This one is minus, minus 1/2. This is 0, and this is negative 1, negative half pi, so it becomes positive again. So, yeah, it's good. And when v is 0, it's 1, right? So log 1 is 0. When this is infinity, it's also 1. So this is 0, minus 1/4 pi. Wow. Finally, I get 2 f of x is f1, I1 plus I2 minus I3. So 2 integral from 0 to 1 f of x dx is equal to I1 plus I2 minus I3. I1, this is I1, okay? This is I1, this is I2. So I1 plus I2 minus I3. Okay, so finally I get this is 3 pi over 4. Therefore, my integral we are looking for is equal to 8, 3 pi. Yeah, this is my final answer.